Everyone, I am Samir Verma and this is third lecture in the series of design of steel structures. Today we will be discussing assumptions in the design of riveted joints, and we will also be discussing the strength of various types of joints, basically the riveted joints. So let us start with the assumptions taken in the design of riveted joints. So what are the assumptions? First assumption is that load is assumed to be distributed equally among all the rivets. So this is an assumption, but in actual what happens that only the outer rivets take more load and inner rivets take less load. But what we assume that the load is distributed equally among all the rivets, which is not true, right? So this happens at the proportionality limit, but when at the collapse, after all the rivets are yielded, then load in all the rivets will be uniform. So after collapse, all the loads in the rivet will be uniform. But at proportionality limit, outer rivets take more load, but inner rivets take less load. But it is an assumption that load is assumed to be distributed equally among all the rivets. Now another assumption is that shearing and bearing stresses are assumed to be distributed uniformly. So we know that there are two stresses, shearing and bearing, in the rivets. So those are assumed to be distributed uniformly. So if this is the cross section of the rivet, then we assume that the shearing stresses are assumed to be distributed uniformly. It is uniform, but in actual it is not uniform. It is maximum at the center and minimum at the ends, or say at the edges. Next assumption is that the bending stresses and rivets are neglected. Yes, we have seen that we have always considered the shearing and bearing stresses, but we have never considered the bending stresses. But if the grip length increases, then the value of the moment becomes significant. So what is grip length? This here we have shown the grip length, that is LG, and the code says that the maximum grip length should not be more than 8 times the diameter, where D is the gross diameter of rivet. What happens if this length, if this grip length is more than 8D, then there will be moments will be generated, and then bending stresses will also be generated. But in actual, while designing, we always neglect these type of neglect these bending stresses. So the code restricts the maximum grip length to be 8D. So you have to restrict your length within this 8D. Next assumption is that friction between the plates is neglected. Again, this assumption is taken. Actually, there is some friction developed, but it is neglected while designing. Next is distribution of direct stresses on the portion of plates between the rivet hole is assumed to be uniform. So distribution of direct stresses, here they are talking about the direct stresses on the portion of plates between the rivet holes. So the portion of the plate between the rivet hole is assumed to be uniform, which is also an assumption. So these were some of the assumptions for designing the joint. Now coming to the next topic, that is strength of the joint. So what is the strength? How will you decide the strength of a joint? So it is taken as the least value of, it will be the least value of three things. One is shear strength of joint against shearing, that is PS, shear strength of joint against bearing, PB, and shear strength of joint against tearing, that is PT, right? So the strength of the joint will be the least of these three, the least of PS, PB, and PT. So that will be the strength of the joint. So let us discuss the strength of joint. First, let us take this joint, lap joint. So you already know that in lap joint we have two plates which are kept one upon another and are connected using the rivets. So there is this tensile force acting on it. We have placed 9 rivets here, 1 2 3 4 5 6 7 8 9 rivets, and it is being connected through this lap joint. So we will be discussing two cases. First case is when we are taking the strength for the entire plate, this plate, and when we are taking the strength for this gauge length, this one G. Fine. So first we'll be taking the case 1, that is for the strength for the entire plate. So You will have to notice this thing that we will be taking only three strength. One is against shearing, next another is bearing and tearing. So the whichever is the least, that will be the strength of the joint. So first let us discuss the strength of joint against shearing of rivet, that is PS. So you know that PS is basically strength, this is force, and you know that force is nothing but area into stress. So it is simple. So you can take area pi by 4 d square into Fs. Fs is nothing but the permissible shear stress. So it will be permissible shear stress multiplied by the number of rivets. So number of rivets here you will have to take 9, because there are 9 rivets. There are total 9 rivets here. 3, 4, 5, 6, 7, 8, 9. So there are total 9 rivets. Then it will be 9 pi by 4 into d square, that is area, into Fs, the permissible shear stress. And the permissible shear stress is taken as 0.4 Fy, you have seen earlier in WSM, and for LSM you can use this formula. Next is to find the bearing strength of joint, right? So bearing strength of joint of rivet is given by, again this is a force, then force is area into the stress, bearing stress. So area, what will we consider? We will consider the thickness of the plate, that is T, and the diameter, that is the gross diameter of the rivet, D. So D into T will be area, D into T will be the area, and FB will be the permissible bearing stress, and N again will be the number of rivets. So T is the thickness of the thinner plate, and PB will be the permissible bearing stresses, right? Next we have PT, that is tearing strength of a plate. So earlier we have seen the shearing strength of rivet, bearing strength of rivet. The third one is tearing strength of plate. So here we'll be discussing the plate, right? So again this is force, so we'll be taking area into the stress. So here area, how we will consider the area? This is taken as B minus N1D times T. T is the thickness of the plate and B is the width. Fine. So how we are taking B minus N1D, I'll be showing you using the diagram. And Ft is nothing but the permissible tensile stress in plate. So how this is coming? B minus N1 times D. So this is width. So if you look at this diagram, then this is the total width of the plate, and 1 is the critical section for the plates. 1 is the critical section. So here you can see that while taking the width, we will be deducting these 3 rivets, 1, 2 and 3 rivets. So diameter of 3 rivets, that is 3D, B minus 3D. So you can see here we have taken B minus N1D, so it is PT equals to B minus 3D. 3D is the 3 numbers of rivets at the critical section, into the thickness of the plate, into the stress. So this way you can find the tearing strength of plate. So the strength of the section will be, the strength of the joint will be the least of these 3. Now let us discuss the case 2, which was the strength of joint or the gauge distance. First we have seen the case 1 was strength of a joint for the entire plate. We have taken it for the entire plate. Now we are taking for the gauge length. This is the gauge length, this one. So instead of considering the whole plate, you will be considering only this part, this one. Fine. So let us see what will be the changes. So again here we will be finding all the 3 stresses, all the 3 strengths. Shear strength of joint or a gauge distance. So PS1 here we are writing. So PS is strength for the shear. So the formula remains the same, pi by 4 d square into Fs. The only difference is that N1 we will be taking. N1 is 3 because there are 3 rivets in one gauge length. So here you can see this is the gauge length, this one. We have 3 rivets in it, 1, 2 and 3. So N will be 3, not 9 here. So the only difference is that the rivets, number of rivets will be 3, 1, 2 and 3, these three. Same way for bearing strength also, formula remains same, dt into fb, that is the same that you have seen earlier. The only difference is that n1 will be taken instead of n. n1 is again 3. Earlier we were taking 9 rivets. Here we'll be taking only 3 because there are 3 rivets in one gauge length. But for the tearing strength of plate, we will not be taking the width of the plate. We will be taking only the gauge length, that is G. And in this gauge length we have only one. See, we have only one rivet. This one rivet at the critical section. Earlier we were taking 3D. Now we will be taking G minus this one rivet. So it will always be G minus D. So you can see here. So it is G minus D times T. This will be the area, and Ft is the tearing strength, permissible strength. Sorry, permissible stress. So here only one rivet is deducted because at critical section 1 per gauge length there is only one rivet. So I have shown you. So strength of the joint will be the least of PS1, PB1 or PT1, whichever is less will be the strength of the joint. So this was the strength for the lap joint. Now second we have strength for double cover butt joint. Again here we'll be taking two cases, for the entire plate and for the gauge length. So here you can see this is double cover butt joint. So these two are main plates and we have two cover plates, one and this one, another one here. So this is the side view and this is the top view of this double cover butt joint. So you can very clearly see here that these are connected using rivets. Fine. So there are two main plates and two cover plates. So I have told you earlier that the rivet will be in double sharing here, one here and one here. So that will be in double sharing. So the only difference will be that if we will find the shear strength of joint, then formula remains the same, pi by 4 d square into fs. The only difference is that it is taken 2 here. 2 is taken because rivets are in double shear. So in lap joint we used to consider it 1 only because it was in single shear, but in this double cover butt joint we have rivets in double shear. So we will be taking 2 and n will be taken as 9 but not 18. So here total number of rivets were 18. See, 1 2 3 4 5 6 and 6 3 is 18. So we have total 18 rivets, but we will be taking only one side of the plate, that is 9 rivets, right? So you'll have to notice this point, that it will be 9. Again, next one is bearing strength of joint. Bearing strength remains same, D into T into FB as earlier, and N will be 9 not 18. You should note it again, it is 9 not 18. And 9, these 9, 1 2 3 4 5 6 7 8 9, not all the 18. You will have to consider only one side of the plate. One thing also you have to notice that this T, so there are in double this type of joint, double cover butt joint, you have, see, thickness, you have two types of thickness here. T1 is for the cover joint, this one and this one thickness, and T2 is for the main plates. So which thickness you will have to consider? In this you will have to consider the sum of the cover plate thickness, that is T1 plus T1, or the main plate thickness T2, whichever is less. So you will be adding both the thickness of the cover plate and the thickness of the main plate, whichever is less will be the thickness here. So either it will be 2 times T1 or T2, whichever is less will be the thickness here to be considered. Next we have tearing strength of main plate. So tearing strength formula is same, B minus N1 D T FT. n is taken 3, n1 is taken 3, because at the critical section 1 there are 3 rivets. Here you can see there are 3 rivets in the critical section 1, 2 and 3, these 3. So we will be taking n1 as 3, and t again will be the thickness of the main plate, that is T2, because we are considering the main plate. Same way, tearing strength of the cover plate. For the cover plate we will be taking b minus 3d, same as before, but here we will be taking thickness will be not T2 but twice T1, that is T1 plus T1, the thickness of both the cover plates into Ft. That will remain the same. So only difference is that here we will be using T2, that is the main plate thickness, and in cover plate we will be using T1 plus T1, that is 2T1, 2 times T1, sum of the cover plates. So one thing we'll have to note, that critical section for main plate is 1, but critical section for cover plate is at 2. So in this diagram you can see that this one is the critical section for the main plate and 2 is the critical section for the cover plates. So there are two types of plates, main plate and cover plates. So we will have to check the tearing strength for both types of plate, cover as well as main. Moving further, taking the case 2, that is strength of joint or the gauge length. Everything remains same. The PS1, the shear strength of the joint or gauge length. The only difference is that again here we will be taking 2 because it is in double shear, and n will be n1. n1 means 3, the total number of rivets in a gauge. So here we can see, here you can see that this is the gauge. We are talking about the gauge strength. So we have 3 rivets, so n we will be taking 3. Earlier we were taking 9, 1 2 3 4 5 6 7 8 9. For the plate we were taking 9, but for the gauge, for this one we will be taking only 1 2 and 3 rivets. So you can see here, see the n1 will be taking 3, total number of rivets in a gauge. Same way, the bearing strength of the joint or a gauge length will be, the formula remains same, except this n replaced with n1. n1 is 3 again, the number of rivets in the gauge. And t, what will be the t? Again t will be the sum of the cover plate thickness, that is T1 plus T1, or the thickness of the main plate, whichever is less. So t you can decide from here. And the tearing strength of the gauge length will be g minus d times t into ft. G minus d because only gauge distance we will be taking g, minus d because there is only one rivet in the single rivet in the gauge distance. Here once more I'll show you. See here, so there is only one rivet in the gauge distance. This is your gauge distance g, and only one rivet is there, this one. So this will be g minus d times the thickness into the ft, permissible stress in tearing. So that was all about the strength of the joints. Now next we are discussing the arrangement of the rivets. So rivets can be arranged in two types. One is chain riveting and another is diamond riveting. In chain riveting we have rivets in the critical section in line to the critical section. See, in chain riveting we have equal number of rivets here, but in diamond riveting we have unequal number of rivets. Like in critical section 1 we have 1, then 2, then 3, like that. So the tearing strength will be, as we have seen earlier, b minus 3d, because b is the width of the plate, minus 3 diameter of the rivet, gross diameter of the rivets, into t, that is thickness of the plate, into the stress of this plate. Fine. And here also you can see that in diamond riveting also, so the tearing strength will be b minus d. Again here b, this is b is the width of the plate, minus d we are taking at the section 1 there is only one rivet, so it will be only d here, t times ft. Fine. So if you look at the tearing strength in main plate, so for in chain riveting you will be seeing that at critical section 1 it is B minus 3D times T into Ft, and at critical section 2 it will be B minus 3D times Ft, the same it was 3, plus in this critical section 2 we will be adding 3 times the rivet value, and rivet value we will be discussing in a moment. So here you will notice one thing, that you will have to add 3 times the rivet value. And in diamond riveting at the cross section 1 here you can see it will be, the tearing strength will be B minus D, because there is only one rivet in critical section 1 so that will be B minus D into T into Ft. And for the section 2 we will be having 2 rivets here, see, 1 and 2, so these are the 2 rivets, so we will be using B minus 2D times T into Ft plus the rivet value, the additional rivet value. So here are some points to be noted. The diamond riveting is more efficient than the chain riveting, because in diamond riveting only one diameter is deducted and tensile strength of the plate is slightly more. Yes, you can see it here, that in chain riveting we are deducting 3 diameters, so the total strength will be less, and here we will be deducting only one diameter, so the tensile strength will be more. Like the width, let us say width is we are taking some width, then we will be deducting 3 diameter, and here we are deducting only 1 diameter, so obviously this one is going to be more, so it is more efficient than chain riveting. Diamond riveting is more efficient. And the next one is rivet value. So what is rivet value? It is taken as the least value of strength of a single rivet in shearing and bearing. So we know that the rivet fails in shearing and bearing, so the rivet value will be the least of the shearing or the bearing value of the single rivet. So which one will be the less will be the rivet value. Fine, we'll see an example. Third, in chain riveting it is impossible for the plate to fail at section 2. Yes, in chain riveting it is impossible for the plate to fail at the section 2. This, here we have 3 rivets, here we have 3 rivets. See, in chain riveting we have B minus 3D times T into Ft, and at the critical section 2 we have this plus this rivet value, 3 times the rivet value. So if it is going to fail, then it will fail in critical section 1, not in critical section 2, because critical section 2 we have additional this value. So this one will always be less. So it will always fail in critical section 1, not in critical section 2. Fine. So next one, in diamond riveting the plate will fail at section 2 if. So in diamond riveting it will fail at section 2 if the condition, see, or if the only condition is that this one is smaller than section 2, the strength at section 2 is less than the section 1. So this is the only one condition when it will be when the diamond riveting will be failing at section 2. So for that we can see that B minus 2D times T plus RV is less than BD into T into FT. So if this is at critical section 2 is less than the strength at the critical section 1, then only the in diamond riveting plate will fail at the section 2. So this is the condition. We will cancel out everything which is common, and this thing will be remaining. Rivet value minus D times T into Ft is less than 0, then plates will fail at section 2. Next point we have, in diamond riveting for cover plate also to be safe, the best arrangement will be, this will be the best arrangement for the cover plates to also to be safe. So like in critical section 1 we have 1 rivet, in 2 we have 2, then another, and at critical section 3 we have again one rivet. So this is formation of a diamond here. Why we are taking 3? Because at 3 also one rivet we are taking, because at critical section for the cover plate only one diameter is deducted. Here also we are deducting only 1 for the cover plate, because this is because 3 critical section 3 is the critical section for cover plate, and 1 is the critical section for main plate. So there is only 1 diameter is to be deducted. So this one is the safest, you can say, the for the diamond riveting. Next topic we have efficiency of joint. So what is efficiency of joint? So again, for the case one, we have entire plate and then the gauge length. So for this entire plate, efficiency will be strength of the joint upon strength of the solid plate. So how can you find the strength? So strength of the solid plate is width into the thickness into the stress, tearing stress. And for the joint, we will be taking width of the plate minus the diameter, sorry, width of the plate minus the diameter into the number of rivets. So that is, you have already seen this formula. So these things will be cancelled out and this formula will be remaining b minus nd upon b. So the efficiency of the joint for entire plate will be this one. And here n is the number of rivet at the critical section. So earlier we have seen n1 was 3 in earlier example. Same way for the gauge length also, strength of joint or gauge, strength of solid plate or gauge. So B here will be replaced by gauge length into the thickness into FT, and in gauge length we have only one rivet to be deducted, so G minus D times T into FT. So the strength of the joint will be this. Again these two will be deducted, thickness and the stress will be deducted, and this thing will be remaining here. So that will define the efficiency of joint. Now coming to the last topic, that is rivet value or bolt value. So rivet value, I have already told that it will be the lesser of the PS or PP, that is sharing or bearing, strength in sharing or bearing, whichever is less will be the rivet value. So in single shear, if there is single shear, it will be pi by 4 D into Fs, you have already seen, and for bearing it will be D into T into Fp. So the rivet value will be least of PS or PP, whichever is the lesser one will be the rivet value. And in double shear, there is only one difference, that you'll have to multiply by 2 because it is in double sharing. So pi by 4 into D square into Fs, and bearing will remain the same, D into T into Fp. So RV is the least, RV is the rivet value, it will be the least of the PS or PP, whichever is the lesser one will be the rivet value. Only thing you will have to notice that the thickness in these two cases, in single shear and in double shear. So for the thickness will be the thickness of the thinner plate in the lap joint. So whichever plate is the thinner one you will be taking in the lap joint, that is T. But in double shear, you'll have to take, there will be double shear, there will be two types of plate, cover plate and main plate. So the sum of the thickness of the cover plate, that is T1 plus T1, or the thickness of the main plate, that is T2. So whichever will be the less will be taken in the double cover butt joint. So that will be the thickness. Fine. So that is all for today. In the next lecture, we will be discussing, or we will be solving some examples in this rivet joint, which we have already seen in previous GATE exams or IES exams. So we will be doing that. So stay tuned for that. Thank you so much.